In this video, we're going to go through the medium level questions on scalars and vectors. As usual, I suggest you have a go at the questions first and then watch the video to check your work or to go through an explanation. Question 1a. Figure 1 shows a uniform beam supported by two light cables, AB and AC, which are attached to a single steel cable from a crane. The beam is stationary and in equilibrium. The tension in cable AB is equal to T1 and the tension in cable AC is equal to T2. The weight of the beam is 9.5 kilonewtons. So first thing you want to do is label on T1 and T2 on AC, and we can pop the weight in as well, 9.5 kilonewtons. Draw a vector diagram to show the arrangement of the forces. So when you draw your vector diagram, you want your forces, we're going to be adding them up in a vector addition. So the end of each arrow should then join onto the next one. So we're going to start with the weight going down. Then we're going to have T1 going up like this. And finally T2 closes our triangle like this. It does say to include the angles. The angles that you've got is T1 is at 60 degrees to the vertical. So you can squeeze a 60 degrees in there. And T2 is at 30 degrees to the vertical. So this will be 30 degrees. It's a bit small there, so I'll do it a bit bigger. And you should end up with a right angle in your leftover corner. Question 1b. Write two equations to show the vertical and horizontal components of the forces in part A. So we'll start with the vertical. I've got a picture of the previous page on the left here so you can see where I'm getting them from. So we'll start with our vertical. So first we've got T1 if we look over here. So T1 has got a vertical component that will come up here. And the angle 60 is between T1 currently and the vertical, so we do cos 60. And that's going to be going up. We're also going to have going up. We're looking at just going up first on this side of the equation. We're going to have T2. And we've got an angle of 30 to the horizontal there. So that's one half of our equation. And that is going to be equal to whatever's going down, which here is going to be 9.5 kilonewtons. So that is your first equation. Your second one is your horizontal. Do our horizontal next. So if you think about T1 here, we've got a vertical component going up and a horizontal going to the right. So we'll do the right first. So we've got T1. Because we used cos 60 last time, what we're looking at is the missing angle here. So you could use cos 30 because the angle is going to be 30, or we can use sine 60. So that's going to be going towards the right. And then towards the left, we're going to have T2 going in the opposite direction. That's going to be going across here at a horizontal, so slightly more straight than that angle. And the missing angle here is 60, so again we could do cos 60. I'm going to do sine 30 because we used cos 30 up here. And there's no other forces going in the horizontal direction, so that's that question done. We are going to use that to calculate the tension T1 in cable AB. And we're going to use simultaneous equations to do that. So the first thing you need to realise is that sine 60, sine 30, cos 60, cos 30, you can just type them into your calculators and they will give you numbers. Once you do that, this seems a lot easier. So I'm going to take this horizontal one, the second one, T1 sine 60 equals T2 sine 30, and I'm going to type sine 60 and sine 30 into my calculator. And what you get is T1, and instead of sine 60, you're going to get root 3 over 2, and that's equal to T2, and sine 30 is a half over 2. So if you look at that, we can cancel that out straight away. So what we've worked out is that T1 times root 3 is equal to T2. We can now take that for what T2 is and put that into our first equation, our vertical equation, and again convert our causes into actual numbers. So every time I see T2, instead I'm going to put this. So I've now got T1, and cos 60 is a half, so T1 over 2, plus T2, I'm going to write T1 times root 3 instead, because that's what we just worked out there, and then cos 30 is going to be root 3 over 2. And that equals 9.5. So I've just taken my value of what I know T2 is and put it into that first equation. You can probably see there's some simplifying here that you can do. So first thing we're going to do is get rid of this divided by 2. So we're going to cross those out. And the way to get rid of that is we're going to times this side by 2. So you end up with T1 plus T1 root 3 times root 3 is actually 3. And we're going to double this side by times it by 2, and you can get 9.5 times 2 is 19 kilonewtons. And what we've got there is 4 T1, because we've got 1 T1 and then we've got 3 T1s here, is equal to 19 kilonewtons. So T1 equals 19 divided by 4, which is equal to 4.75 kilonewtons. That is your final answer for that one. And finally, we've got to calculate the tension T2 in cable AC. That's really easy now because a minute ago we worked out up here that T2 is equal to root 3 times T1. So we just take that T1 value and we times it by root 3. So 4.75 kilonewtons times root 3, and you get 8.22 kilonewtons. Everything in this question was to two significant figures, so we should probably round that at the end to two significant figures, so you get 8.2 kilonewtons instead. So in question 2a, we've got a helicopter, and it has got a lift force which is labelled A and is 12 kilonewtons. So I'm going to draw that on here straight away as I go through my question. And it acts at an angle of theta to the horizontal. At any point the lift force, which is A, is 4 times larger than the drag force. Draw a vector diagram. So we're going to start with C going down, that's the easiest. Then we're going to do B coming out of that one, going across. So if you have a look, C does go down and B goes across towards the right. And then finally we can join those up with A, our 12 kilonewton force. And we can label theta as well. So we know that theta is this angle here because up here it's shown to the horizontal, and this is from A to the horizontal. Part 2b, show that the angle theta is about equal to 76 degrees. So to do this we can use our triangle again. I'm just going to draw it again, but this time we're going to add some numbers onto it. So this is theta, this is what we're trying to work out. So A, we know from the question, is 12 kilonewtons, so I'm going to put 12 on there. We also know the value of B because the question says at any point the lift force is 4 times larger than the drag force. So B is our drag force. That's what's preventing it from moving. It's going against it as it tries to move horizontally. And we know that what we've got already, our lift force, is 4 times larger than that. So we do 12 divided by 4 equals 3. And this one here is 3. So we've now got a triangle with two sides labelled and an angle. So if we use a bit of trigonometry, I'll just do it in a different colour. This is our opposite, this is our hypotenuse, and this is our adjacent. And we are missing, we haven't got our angle, and we haven't got anything for the opposite. So we're going to be using A and H, and if you remember from trig, that one is cos. So the cos of the angle is equal to the adjacent over the hypotenuse, and we want that angle. So to work out the angle, we do cos minus 1 of the adjacent, which is 3, divided by 12. And if you type that into your calculator, you get 75.5 degrees, and everything's to two significant figures here, so that rounds to 76 degrees. Question 2c, calculate the weight of the helicopter and give your answer to an appropriate number of significant figures. So we know from the previous page that the angle is 75.5 degrees, or around that. And to work out the weight of the helicopter, so we know that the vertical component of A, whatever force is going up from A, has got to be equal to the weight going down for it to continue to remain in equilibrium. So therefore, A sine angle, not cos the angle, because that would give us our horizontal component. We know that A sine angle has got to be equal to the weight going down. So to work out our weight, we take our value for A from the previous page, which was 12 kilonewtons, 12,000 newtons. We times it by sine 75.5 and we get 11618 newtons. And it says to give it to an appropriate number of significant figures, which this question, having a look back at the previous one, is 2 or 3 significant figures would be appropriate. Newtons. And question 2D, the helicopter begins to descend at a constant speed at an angle of 15 degrees to the horizontal. Draw a vector triangle to show these new forces. So we'll start with the weight, because that's going to be exactly the same. C, which was our weight. A, our force is actually going to be very similar. The only thing that's going to change is our drag force, which previously was horizontal. It's now going to be at 15 degrees to the horizontal. 15 degrees to the horizontal. That is B. And A is going to end up being very similar coming up here. Question 3A. So we've got a figure that shows two forces acting on a ladder against a vertical wall. We've got a resultant force pushing against the wall, and we've got the weight. Explain how it shows that there is no friction or that the friction is negligible. So if we had the friction, it would go along the vertical component, but we don't have anything there. So the fact that we have a resultant force that is coming horizontal or is at a right angle to the wall and no mention of a vertical force shows that there is no friction. Question 3B. The forces are in equilibrium. Draw an arrow to show the direction of the resultant force. On the ground, label your arrow G. So the best way to think about this question is to draw a triangle by the side. I'm going to start it over here. So we've got our weight going down. We've got our resultant force coming this way, which I'll call R. And then we've got our final force, which is going to be G up this way to close that triangle. So your G is going to be sort of like that to close your triangle. Question 3C. The reaction at the ground acts at an angle of 60 to the horizontal and the ladder weighs 140. Calculate the magnitude of the resultant force G from the ground acting on the ladder. So we're going to draw our triangle again. This time we've got 140 newtons going down. Going to put that on the other side actually. You've got 140 newtons going down. You've got your unknown force going across, your resultant force, sorry, and then we've got G coming up like this. The angle that we know is to the horizontal, so that was 60 degrees to the horizontal. And now we just have to use trigonometry. So in another colour again, I'll do it to label our sides. We've got the opposite of the angle. This is our hypotenuse, and we have got the adjacent down here. The question is asking us to find G, so we're working with the hypotenuse and the opposite, which is sine. If we draw a little formula triangle like this. So the sine of the angle, which here is 60, is going to be equal to the opposite, which is 140, divided by our unknown force G. You are going to type into your calculator, and you'll get an answer of 161.6 something something, which is about 162 newtons. Going on to part 3D. If the wall was removed, only the weight and the reaction at ground G would act and the ladder would begin to topple. State the direction of resultant force R and calculate its magnitude. So our resultant force is what's going to make it topple. We all know it's going to topple sort of this way. It's going to end up going down. So our force R is going to be horizontal. Horizontal. And it's going to be to the right. So work out its magnitude. We can draw a formula triangle again. We've got our weight coming down. This time we've got R going this way. And we've got G coming up like this. To work out R, we can use Pythagoras theorem, but we're not working out the hypotenuse this time, so we're going to have to rearrange the Pythagoras theorem. So usually we'd say G squared is equal to R squared plus W squared. So we're going to have to rearrange to find R. So you'd get R squared is equal to G squared, take away W squared. So what you're going to type into your calculator is going to be the square root of g squared, which is 162 squared, take away the weights, which was 140 squared, and you end up getting something that rounds up to 80.8 newtons. Question 4a. Figure 1 shows an uniform steel girder being held horizontally by a crane. 2 cables are attached to the ends and the tension is T. Draw an arrow to show the line of action of the weight. So the weight is just going to be going down. For now we're going to presume it's in the middle. It says it's uniform, so the weight always acts in the centre. Then we're going to calculate for 4b the tension in each cable. Oh no, we've been given the tension, it's 650, I'll put that on there. We need to calculate the horizontal component of each one. So it's going to be just 650, the angle is here, so cos 48, which is equal to 430 newtons. I've rounded that to 2 significant figures, and the vertical component, 650, you can do cos 90 take away 48, or you can just do sine, and then we get 483, so let's round that to 480 newtons, because everything's been given to us here in 2 significant figures, so that's sensible. Question 4d, calculate the weight of the girder. So I've brought across our data from the previous question. So both of our vertical components of the tension was 480. That is rounded to 2 significant figures, but you get the idea. We've got 2 lots of 480 going up. To balance that out going down, therefore we must have 2 times 480, which is going to be 960 newtons going down. Okay, question 5a. Figure 1 shows a 500 kilogram iron ball being used on a demolition site. It's suspended by a cable, which makes an angle with the vertical, and it's pulled in position by a rope with tension 1,600 newtons. Determine the magnitude of the vertical component and write an expression relating angle theta with the vertical and t. So first thing you need to know, we've got a mass, but we haven't got a weight. So to turn that mass into the weight of our ball, we need to times it by the strength of gravity. So we'll take our 500, we'll times it by 9.81, and you will get a number that is around 4,900 newtons. So that is the weight of our ball, 4,900 newtons. That's what we're going to use for the rest of the question. And if that's our weight going down, we must also have that force going up somewhere to keep it in equilibrium. And that's got to come from the tension. So we know if we resolve this tension going vertically, T cos angle has got to be equal to 4,900. So what the question asks is to write an expression relating the angle with the vertical and T. So I'm just going to rearrange that to give what T is. T is equal to 4,900 divided by cos angle. That is all this question wants. Question 5b, determine the magnitude of the horizontal component of the tension and write an expression relating the angle with the vertical and T. So this is very similar to our previous question. So to work out the horizontal component of T, that's going to be down here. So instead of T cos angle, it's going to be sine angle, and this time it's going to be equal to whatever is going in the opposite direction, 1,600 newtons. To do question 5c, I personally would draw a formula triangle with everything we know. We've got the weight going down, we've got the rope force going across, and then finally we've got the tension closing up our triangle, and the weight we also know is 4,900, and it wants the angle with the vertical, which is this one here. So we're going to be doing some trigonometry again. So this is our opposite side. This is a right angle, sorry, this is our adjacent, and this is hypotenuse. We want nothing to do with the hypotenuse, we just want to use O and A, which is tan. So the tan of the angle is equal to the opposite divided by the adjacent. So to work out our angle, we do the tan minus 1 of 1,600 divided by 4,900, and you get 18-ish degrees. And finally, determining the magnitude. Hopefully we know how to do this by now, it's just Pythagoras theorem. So to get our magnitude, we're going to do the square root of both those sides squared and added together. and you should get an answer, 5,200 newtons. Well done if you managed to get any of that by yourself. These are really, really challenging questions, so even if you just watched along and vaguely understood what's going on, you've done really well. As always, come see me if you have any questions.